In the mathematical field of descriptive set theory, a point class is a collection of sets of points, where a point is ordinarily understood to be an element of some perfect Polish space. In practice, a point class is usually characterized by some sort of definability property. For example, the collection of all open sets in some fixed collection of Polish spaces is a point class. Point classes find application in formulating many important principles and theorems from set theory and real analysis. Strong set-theoretic principles may be stated in terms of the determinacy of various point classes, which in turn implies that sets in those point classes have regularity properties such as Lebesgue measurability, the property of Baire, and the perfect set property. Basic framework. In practice, descriptive set theorists often simplify matters by working in a fixed Polish space such as Baire space or sometimes Cantor space, each of which has the advantage of being zero-dimensional, and indeed homeomorphic to its finite or countable powers, so that considerations of dimensionality never arise. Moshevakis provides greater generality by fixing once and for all a collection of underlying Polish spaces, including the set of all naturals, the set of all reals, Baire space, and Cantor space, and otherwise allowing the reader to throw in any desired perfect Polish space. Then he defines a product space to be any finite Cartesian product of these underlying spaces. Then, for example, the point class of all open sets means the collection of all open subsets of one of these product spaces. This approach prevents from being a proper class, while avoiding excessive specificity as to the particular Polish spaces being considered. Boldface point classes. The point classes in the Borel hierarchy, and in the more complex projective hierarchy, are represented by sub- and superscripted Greek letters in boldface fonts. For example, is the point class of all closed sets, is the point class of all F-sigma sets, is a collection of all sets that are simultaneously F-sigma and G-delta, and is the point class of all analytic sets. Sets in such point classes need be definable only up to a point. For example, every singleton set in a Polish space is closed, and thus, therefore, it cannot be that every set must be more definable than an arbitrary element of a Polish space. Boldface point classes, however, may require that sets in the class be definable relative to some real number, taken as an oracle. In that sense, membership in a boldface point class is a definability property, even though it is not absolute definability, but only definability with respect to a possibly undefinable real number. Boldface point classes, or at least the ones ordinarily considered, are closed under Wad reducibility, that is, given a set in the point class, its inverse image under a continuous function is also in the given point class. Thus a boldface point class is a downward closed union of Wad degrees. Lightface point classes. The Borel and projective hierarchies have analogues in effective descriptive set theory in which the definability property is no longer relativized to an oracle, but is made absolute. For example, if one fixes some collection of basic open neighborhoods, then the open, or, sets may be characterized as all unions of basic open neighborhoods. The analogous sets, with a light face, are no longer arbitrary unions of such neighborhoods, but computable unions of them. A set is light-faced if it is the complement of a set. Thus each set has at least one index, which describes the computable function enumerating the basic open sets from which it is composed. In fact, it will have infinitely many such indices. Similarly, an index for a set B describes the computable function enumerating the basic open sets in the complement of B. A set A is light-faced if it is a union of a computable sequence of sets. This relationship between light-faced sets and their indices is used to extend the light-faced Borel hierarchy into the transfinite, via recursive ordinals. This produces that hyperarithmetic hierarchy, which is the light-face analog of the Borel hierarchy. A similar treatment can be applied to the projective hierarchy. Its light-face analog is known as the analytical hierarchy. Summary. Each class is at least as large as the classes above it.